Hello everyone, today's guest is Dr. Tamara Bogdanovic, an astrophysicist and professor at Georgia Tech who studies supermassive black holes and uses computational modeling to understand gravitational waves and cosmic collisions. She's received a number of accolades for her research and teaching, including the Sloan Research Fellowship and the Einstein Postdoctoral Fellowship. Today we'll be talking about LISA, the big upcoming gravitational wave experiment. This was recorded on April 9th. Please welcome Dr. Tamara Bogdanovic. So how about you start by explaining for the listeners what LIGO is, how it works, and what LISA is?
So both LIGO and LISA are gravitational wave interferometers, which means that they use the technique called interferometry, superposition of signal, effectively, in order to detect a passing gravitational waves. And in order to have a superposition of signals, one needs to detect the signal in at least two channels, basically, in order to combine it and compare it and find the signature of a passing gravitational wave by effectively detecting whether one channel or one arm of the interferometer has shrunk in some way that can be predicted and explained basically by a passing gravitational wave. And what we really measure, we measure the light travel time of light down the arms of the interferometer, and we compare those signals. So we measure how much shorter or longer the arms became due to the passage of the gravitational wave, which stretches and compresses the space-time by effectively shooting lasers down the interferometer arms and measuring the time that it takes them to cross from one point in the arm to the other, from one end to the other. Yeah. So that's the technique that is currently used to detect gravitational waves in LIGO. That is also the technology that will be used in the future space-based gravitational wave detector LISA. LISA stands for Laser Interferometer Space Antenna. So that will again be done, but in space this time. So, yeah. So those are the similarities and some key differences between the two.
Mm-hmm. And so LISA is planned for launch in 2037, I think?
It's actually, the year was a little bit more precisely determined very recently when LISA was selected by the European Space Agency and was given a go-ahead, basically. The LISA team was given a go-ahead to build the spacecraft and the detectors, and the launch time is now pinned to the mid-2035. Yeah, so a little bit sooner, but it's exciting that it's getting a little bit more concrete and more precisely scheduled.
Nice. And so it'll be orbiting the sun, right? Like in the orbit of Earth, kind of?
That's right. So LISA will be a constellation of 3 spacecraft, and they will be launched in such orbit that they will be trailing Earth on its orbit around the sun. So each individual spacecraft will have a heliocentric orbit, will be moving around the sun, but in such configuration that will resemble a triangle that is effectively tumbling on its orbit and it's following Earth. It will be a formation of 3 spacecraft.
So what types of gravitational wave sources will LISA be able to detect that current detectors can't, and why?
So LISA will be able to detect gravitational waves with very long wavelengths, and that means with very low frequencies, right? So compared to LIGO, that detects gravitational waves with like 100 hertz or 1000 hertz, LISA will be most sensitive in the millihertz gravitational wave band. And that means that it will detect slightly different type of sources from LIGO. So LIGO presently detects collisions of compact objects of stellar origin, like neutron stars and stellar origin black holes, which have masses anywhere between a solar mass to a few hundred solar masses. LISA will be detecting gravitational waves from such types of binaries in our galaxy, but not at the point of merger, but at the point when they're more widely separated and or their orbit is evolving more slowly. So there will be a whole lot of such binaries in our own galaxy, the Milky Way, that LISA will be able to detect. In addition to those sources, LISA will, for the first time, detect gravitational waves from supermassive black hole binaries, those that have masses in excess of 10 to the 4 or 10,000, 100,000 solar masses, with the highest masses probably corresponding to 10 to 100 million solar masses. And that is a sight that we've never seen before, so that will be an exciting new discovery. LISA will also detect smaller stellar origin compact objects like black holes orbiting around very large supermassive black holes, those with mass of 10 to the 4 all the way to higher, 10 to the 6, 7, 8 solar masses, and so on. So those are some of the expected sources that we know are there in the universe, but we also hope to use LISA to test our understanding of the cosmological model and also to perform some tests of fundamental physics, basically, to measure the speed of gravity relative to the speed of the photons and so on. So there is a whole range of experiments that we hope to carry out with LISA to understand how black holes form in the universe, how they evolve, how they grow in their host galaxies, but also to perform these tests of cosmology and fundamental physics at the same time, using those detections and measurements.
Yeah. Explain why exactly the long arms allow for detection of lower frequency waves.
So longer arms are beneficial in all cases because they allow a longer path length for the light traveling down the interferometer arms, which means that you can accumulate more difference and measure a bigger difference due to the passage of a gravitational wave. The arms are being stretched and shrank in concordance with space-time being stretched and shrunk by the passage of the gravitational wave. So obviously, the bigger the time difference that you can measure, the stronger the signal. However, in practice, you're limited by how long the arms can be. For ground-based interferometers, you're limited by the amount of space that you have on the surface of the Earth, because it's quite costly, right, to build those interferometric arms, which for LIGO are basically dug down into the ground, and they reside in vacuum cavities and so on. So in principle, you do want longer arms, but in practice, there is some middle solution that is found as a compromise between cost and sensitivity that can be achieved.
The primordial gravitational wave background is thought to be primarily caused by inflation, right? The rapid period of expansion that the universe is thought to have gone through early in its history.
Mm-hmm.
So LISA could basically confirm inflation, or at least provide very strong evidence for or against it.
I actually am not sure if this is not my area of expertise, and I'm not sure to what degree will Lisa actually be able to constrain the inflation. But um, this gravitational wave emission from the early universe, if indeed it's there, will also be superimposed with gravitational wave emission from all different sources. So the one thing with LISA is that when it detects gravitational waves from the sky, it will detect it simultaneously from many, many different sources. And in some parts of the spectrum, there will be so many sources that they will effectively create a continuum of the so-called gravitational wave background. So in some other parts of the spectrum, if the sources are loud enough in gravitational waves, they will appear as individual sources, signal from individual sources on top of that background. So detecting any particular signal from any particular source for LISA means understanding signal from all the other sources so that it can be decoupled and explained. So to the degree that that's possible for basically primordial gravitational waves from the early universe, basically to that degree, we'll be able to constrain it.
So if Lisa detected a stochastic gravitational wave background, what specific analysis techniques would distinguish between primordial sources and unresolved astrophysical sources? Like just a bunch of mergers from across cosmic time?
So those techniques are actually currently under development because they will have to model at the same time the signal from known sources and signal from unknown sources. So in order to discover basically signal from anything that is not expected or it's not clear whether the signal is there or not, one will first have to subtract all the types of the signal that are known and identified, right? And expected. So one would have to subtract the individual supermassive black hole binary sources. One would have to subtract signal from stellar origin black holes and intermediate black holes, and as well as other compact binaries in our galaxy, which include also white dwarfs and neutron stars and black holes and all that. So when that is all done, and we're talking about this dynamic signal that changes in time, when that all is done, what's left, the residual in the spectrum, will then be considered in terms of basically these other sources that could be primordial gravitational waves from the early universe and some other perhaps unexpected sources of gravitational waves. That's my understanding of the analysis. So as I said, that analysis is currently still under development for LISA.
Mm-hmm. And although it might not be your area of expertise, could you explain why primordial gravitational waves would be so significant if found?
Well, we never detected gravitational waves from the early universe, and we have a lot of questions about those early stages of the universe that we cannot investigate using the other messengers that we're able to detect, like the light or particles like cosmic rays, charged particles that are moving at relativistic speeds. So gravitational waves will have easier time traveling to us from those early days of the universe. So that makes them an interesting new tool, an interesting new way to peer into the early general universe and measure its properties. So I think that's their greatest advantage.
Mm-hmm. The CMB can only tell us, or can only give us information as old as about 380,000 years after the Big Bang, because before then the universe had a very high opacity and photons weren't able to travel very far before scattering, whereas gravitational waves could provide a window into what was going on 10 to the negative 32 seconds after the Big Bang. So it's a huge difference.
Mm-hmm.
What are some of the more crazy things that Lisa could potentially discover? Perhaps, for example, modifications to Einstein's general relativity, or would it be able to maybe say anything about more exotic theories like quantum gravity or string theory?
So Lisa will, and its detections will be used to test the theory of gravity. So the prevailing paradigm that we are using is the Einstein's theory of general relativity, which so far has passed many different tests, whether indirect, meaning tests that have been done with electromagnetic observations, or more recently direct tests by measuring gravitational waves. And but that is a continued process, and we will continue to test GR with high precision measurements that we expect to obtain with LISA and have not been able, for example, to obtain with LIGO. So yes, there are alternative theories of gravity will be tested, and perhaps other theories, quantum gravity and the string theory, as long as we basically get gravitational wave emission at the level that allows us to perform those tests.
Do you know like what specific signatures we would look for those types of things?
So for alternative theories of gravity, basically researchers look for departure in the gravitational waveforms from what you would expect based on the predictions of Einstein's theory of general relativity. And in some cases, those changes are subtle, the way that they change the shape of the gravitational wave or its phase. So again, one needs to achieve a measurement with a sufficient signal to noise ratio in order to be able to extract that information. But the methods, the methodology is being developed and designed to basically perform those tests with LISA detections.
Mm-hmm. And so what work have you specifically been doing with the LISA collaboration?
So within LISA collaboration, I've been investigating the prospect for detection of gravitational wave sources, specifically supermassive black hole binaries, which will also be accompanied with an electromagnetic signal or counterpart. And we expect that supermassive black hole binaries will be a source of both gravitational waves and electromagnetic radiation if they're immersed in gas accretion flows. So that gas accretion flows basically serves as luminous tracers of otherwise dark supermassive black holes. And the reason why this is of interest is that by detecting supermassive black hole binaries using two messengers as opposed to only gravitational waves, we stand to learn more. And we stand to learn more physics, and we can learn much more about not only the black hole binaries themselves, but about their contextual place in the universe, right? In the context of their host galaxies, which we can observe and detect using light and electromagnetic radiation. So, yeah, that's a good way to connect the story of massive black holes in our universe to the story of the rest of the universe, galaxies and groups of galaxies and so on.
How will the massive amount of data LISA produces be handled?
So that data will have to be channeled from the instruments and the spacecraft to the ground, and that will, to my understanding, happen periodically. So LISA will not be necessarily in contact with laboratories on Earth all the time. I think that the information will be downloaded with a certain cadence, but what that cadence is, I believe, is still being determined. In a sense that it should not be too rare of an occurrence so that you miss basically a gravitational wave event that is happening at that point in time, or you miss the chance to follow it as it in spiral, as the two objects in spiral toward merger. So yeah, it will have to be buffered, and the data will have to be buffered and then downloaded from the spacecraft to Earth periodically. Basically, I think that that's the plan. The last I heard of it.
So the implementation of this experiment is also very interesting because it seems like an incredible feat of engineering when you think of these three objects that are traveling so quickly in sync. How do they maintain the same distance from each other so consistently? And what are the biggest engineering challenges, as far as you know, in maintaining this precise spacecraft positioning?
Right. So my understanding is that LISA, the three spacecrafts that make the LISA observatory, they will be flying information, but not necessarily at distances that have to be exactly the same at all points in time. The key point will be to have an accurate measurement of the distance from one spacecraft to another at the point when the detection is made, right? So in order to understand that signal superposition, that's the information. So it's not so much important for spacecraft to have identical separation from one another, but it's certainly important to measure that distance very precisely. And I think that flying information is the new capability that has been developed in the past decade, or the decades that has not necessarily been available at the time when LISA was envisioned. And it definitely includes a lot of precision in formation flying. So certain precision has to be achieved in formation flying, but not only in formation flying, also in our ability to measure the signal to very high precision, and that change in length of the interferometric arms. So that is also something that has been achieved only more recently and after the LISA was proposed as a concept. Some other technology breakthroughs were demonstrated with the LISA Pathfinder. This was a spacecraft which was launched to basically demonstrate that key technology that LISA will depend on, the whole mission will basically be relying on, is possible to realize. And part of that was that we're able to keep the test masses that are used to basically measure that signal, interferometric signal, that or they're used to measure that one arm of the interferometer is getting stretched or compressed relative to the other. In order to make that measurement, one needs to maintain a test mass, which is basically a massive cube of about 2 kilograms made of gold and platinum, and it needs to be in free fall. So basically, as the three spacecrafts are orbiting around the sun, the test masses will be floating and will be kind of encased in a cavity within which they will be floating without touching the walls of the cavity. So that needs to be done and realized to, again, very high precision with very low levels of noise. And in 2015, the LISA Pathfinder demonstrated that can be done with an extremely high precision. So that was a very important step, basically, in realizing the LISA mission, because it was the whole mission was hinging on that demonstration of technology. So those are some of the key technology developments that needed to happen in order for LISA to be adopted and approved by the space agencies that are involved in this mission.
And Earth's orbital velocity is about 30 kilometers per second, so that's about how fast they're traveling, right?
Mm-hmm. So yeah, because the satellites will be trailing Earth and at a relatively constant separation from Earth, yeah, they will be flying with a comparable orbital velocity, yes.
How will the launch and deployment process work? For example, will they all be launched together on one rocket and then released once they're in orbit?
So that is a very interesting question to which I only heard the answer like about a week ago when we received the news that the European Space Agency has finally selected the contractor that will build the spacecraft. So those contractors basically proposed the design of the LISA spacecraft, and the design then implies how the spacecraft will be effectively packed together and launched within a rocket. So my understanding based on that is that they will be stacked on top of each other, all three, and they will be released one by one. So they're using propulsion systems, their orbits will be corrected until they are in the formation of a triangle, the formation that is planned for them. But I think that that's really kind of a mesmerizing prospect of how you launch a configuration of 3 spacecrafts, put them on the orbits that they should be on, and then it will take some time to basically get them in the right place and to start turning on the instruments and detectors, which will start taking the scientific data. So that should all happen sometime in 2035.
Interesting. What advantages does LISA have over LIGO and other ground-based detectors? I know one of them is that it doesn't have to deal with all the seismic noise. Perhaps you could explain that, and then if there are any others, explain that too.
So one advantage, an important advantage that you mentioned is the absence of the seismic noise, right? So for instruments like or observatories like LIGO and LISA that are making very high precision measurements, it's very important to keep the noise and vibrations from the environment to the minimum. And that includes not only the parts of the detector, which are lasers. Lasers, in principle, can be noisy. Electronics that is involved can create its own noise, but also the external environment. And for ground-based detectors, they're clearly and inevitably coupled to the environment where they're placed on Earth. And on Earth, there are a lot of sources of noise. So there are a lot of vibrations that are created by all kinds of things. The traffic, the humans moving, the trees being fell down, earthquakes, right? Motion of the oceans, things like that. So that is something that ground-based detectors have to deal with, and they have to find creative and good ways to filter out the noise that is undesired, right, and can pollute the signal. Obviously, for space-based observatories, they don't have to deal with the seismic noise and human noise, if you wish, but they have a different challenge, right? And the challenge is that of being launched to space successfully. Another advantage that comes from being in space is that interferometer arms can be much, much longer to basically optimize the sensitivity of the instrument while still maintaining a manageable cost to the mission. That's very hard to do on Earth because longer arms of the interferometer for ground-based detectors inevitably mean a much bigger cost. And at some point that cost becomes prohibitive. So the length of the interferometric arms is basically a compromise between the desired sensitivity and cost of the mission. And there's much more space in space, right? So it becomes a little bit easier to create a bigger detector and still maintain the cost reasonable, as long as the technology can basically function and at those very large separations, which for LISA, the interferometric arms will be of length of 2.5 million kilometers. And for LIGO, for example, in comparison, those arms are 4 kilometers long.
Mm-hmm. If aliens were building a gravitational wave detector, what might they do differently from LISA? For example, like if they had far more resources than we do?
So I'll take the question to mean, if we had unlimited resources, would we build and design LISA differently? And I don't know, if we had access to more advanced technologies, perhaps, would we do anything differently?
For example, maybe the scale or the positioning of the satellites, or I'm not sure.
That is a good question. Can you imagine having more than 3 spacecraft? And I can imagine having basically spacecraft not only operating in the millihertz gravitational wave regime, or for LIGO, hundreds of hertz or kilohertz, but everywhere in between and around it. So perhaps with plentiful resources, we could cover the entire gravitational wave spectrum by basically creating detectors that can detect gravitational wave signal there. Another thing is that the data would be coming to the ground segments on Earth, basically the labs where the data will be received continuously, instead of having certain times when the data will be downloaded. The data would just be streaming in real time. So that's the first thing that comes to mind. Basically, more spacecraft instead of just 3, perhaps multiple. And they would also have pretty good sky coverage in all other messengers, like neutrinos and also photons, which would give them a complete picture of the multi-messenger sky. So that's what I envision.
Do you have any idea how gravitational wave astronomy might evolve in the decades after LISA?
Potentially. So obviously, LISA and observatories that will be contemporaries with LISA will be flying sometime in the mid-2030s. And the time that it takes to plan and execute such ambitious missions is usually about 20 to 30 years. So it takes about 20 to 30 years to build very large space-based observatories, and that's typically the cycle on which international space agencies will review their portfolio and their plans for basically the future space missions. So for NASA, that happened, the last time it happened was in 2013, when they released their plans for space-based observatories for the next 30 years. And for the European Space Agency, for example, that report was released a couple of years ago. It's called Voyage 2050, and its goal is to basically envision what kind of spacecraft will be built in following LISA. So sometime after 2035, plus 20 years into the future. These types of reports also review what kind of technologies are available, what kind of technologies will need to be improved, and what kind of technologies will need to be developed from scratch in order for some of these to be possible, some of these missions to be built. And also, they also consider what kind of new scientific breakthroughs will be necessary in order to, or what kind of scientific breakthroughs will be possible with these new technologies and new generation of spacecraft. So I am a part of one such group that is considering what might be the future of gravitational wave astrophysics, or what will be the landscape of observatories in the 2050s, where the European Space Agency basically commissioned this report, and their charge is to investigate the high redshift universe, basically in the 2050s, using those such observatories. So a part of that is to consider again what types of scientific breakthroughs will be possible with gravitational wave missions if, for example, they will be detecting gravitational waves in a microhertz band, which presently is not explored by any gravitational wave observatories or concepts, and it's actually a lower frequency band than what LISA is expected to detect, which will be sensitive in the millihertz gravitational wave band. Alternatively, an observatory can again be detecting millihertz gravitational waves, but perhaps it may be much more sensitive than LISA. And it's this group of people who are working on the report that I mentioned are considering how that impact basically the science that we can do. What new discoveries can we make if we had an observatory like that? And finally, one can also envision a space detector that would detect gravitational waves in the decihertz band, which would be frequency that is higher than that the LISA will detect, but it's lower than what LIGO can detect. So it would basically cover that part of the gravitational wave frequency band that sits in between LISA and LIGO. So those are some of the considerations. The selection process has not been made yet on the side of the European Space Agency, and for NASA, I think the plan or the report for the next 30 years is yet to be made for that time span of 2050s and beyond. So that's, yeah. that's the outlook and planning, right, that is happening in this stage.
Given that this is, as you mentioned, a big international collaboration between the ESA and NASA that's been in development for decades, do you have any opinion on what lessons the scientific community has learned from trying to launch a nearly 2 billion euro space interferometer?
Well, the lessons are, I guess, that a very big undertaking like this will always have to be a partnership between many different nations and many different space observatories, and such partnerships they're very important for success of missions like LISA, but they're also subject to all kinds of international politics that affects, right, the different countries. And I think just like all other endeavors, it takes a lot of work and a lot of collaboration to make them come true and to have them be successful. So I think that will be important to maintain
Mm-hmm.
in the future as it is now.
Yeah. Would a private company like SpaceX ever be able to do something similar faster?
Um, I'm not sure. Maybe one day. I mean, at this point in time, they certainly can build spacecraft, and they can build them very quickly and in innovative ways. What I would say is that that's one component, right, of scientific missions. You also need scientists, right, who will help make the breakthroughs, and who will be motivated to develop new technologies even before they can be commercialized. So when there is no obvious commercial benefit just yet, right? There. So I think that scientists and scientific community and um, engineering community, they're all very important components that have important roles in these big scientific missions.
Speaking of that, in a world where scientific talent is increasingly pulled towards AI or startups, how do we keep ambitious people working on missions like LISA?
That's a good question. That's a tough question. I think that there will always be people who enjoy doing fundamental science, and they enjoy working on problems that no one has worked on before, and basically pushing that frontier of our understanding of the universe, our understanding of the laws of physics or laws of science. And it's important to actually have missions like LISA that will provide the space to train those young scientists, and they will also motivate them to research further, right, into these questions, into fundamental. So I think as long as we have that, we'll always have people who are interested in, because yes, nowadays it's perhaps AI, it's startups. Before that, it was I don't know, perhaps banking and financial sector that were very attractive to many other young scientists and researchers with technical training. So what I want to say is there always have been and there always will be some other appealing options, and that's perhaps not a bad thing, right? Because those young researchers will be able to contribute to the society in one way or the other, and they will have the choice of which way to go.
Mm-hmm. Awesome. Well, yeah, I'm excited to see what Lisa finds. It's a very fascinating experiment, and yeah, thank you for coming on.
Thank you very much for having me.